Now we're going to get into the electron energy levels. It turns out that we don't just have a nucleus with electrons just wherever around it, orbiting around. It turns out that, like you've probably seen models of the atom before, that those electrons orbit on specific rings. And although they are in reality three-dimensional, which is what that symbol is kind of trying to show, frequently we will flatten them out so that they look kind of like orbits of planets, and imagine those are actually circles and nice neat ovals there, and we will treat them like that. But it turns out the electrons can only exist on those rings. They can't exist on the spaces in between. And you're going to be able to do the electron arrangement for the first 20. If you have me live, I'll show you a little bit how you do the higher levels, and we'll get into the different notations for that. Before we can do that, we need to talk a little bit about light itself. So light is also known as electromagnetic radiation. It turns out that light is a wave, and that wave actually has an electric wave and a magnetic wave that are at right angles to one another and then move in a third angle. So there's a up and down vibration that, let's say, is the electric wave, and then there is a in and out vibration that is, let's say, your magnetic wave, and then there's a motion in that direction. So all three are at right angles to one another. And although we tend to think of it as just visible light, there are all sorts of other types of light, from radio to microwave, infrared, visible light, ultraviolet, X-rays. There's an even higher one called gamma rays. And there's all sorts of different types of light. When you have a wave, the distance between your peaks, which, if I took the time and actually was careful with how I drew, would also match the distance between the valleys, or the distances between, say, a midpoint, and here I'm going up and back down, and here where I'm going up again, I'm matching midpoint. Any one of those could be considered a wave, a chunk of the wave, and we call that the wavelength. Because it's a length, we actually use an L kind of to abbreviate it, but we use the Greek lowercase l, which is a lambda symbol, kind of looks like an upside down Y, but you don't need to worry about that specifically. But it turns out that high energy radiation, so high energies, have short wavelengths, and low energy radiation have long wavelengths. When we have opposites like that, it's called a inverse relationship. Now, there's a really easy way to memorize this. Take a rope and shake it such that you get waves on it. Think a jump rope, maybe, and shake it so that you get waves on it. If you want to have those waves be closer together and be shorter, you have to shake a lot faster. Well, that takes more energy. Short wavelength, high energy. If you want longer waves, then you don't have to move as fast, less energy, longer waves. It also turns out there's another thing in there called frequency, which is how frequently or how often they come by. It turns out that high energy is high frequency, and that low energy is low frequency. And sometimes you'll see frequency abbreviated with an F, and sometimes you'll see it abbreviated with the Greek lowercase n, which is called nu, and looks like a kind of cursive V. So on this one here, you can actually see the wavelengths listed, you can see the frequencies listed. They then just say low and high energy. We could put numbers to those, it's really easy, but again, if you're live, I'll show you how we do it. We may even do a lab over it if time allows, certainly a demo. Anyway, we have low energy to high energy there. Notice the wavelength here starts out long. We have 10,000 meters, and then down this way we have 10 to the negative 11. That's a whole bunch of zeros. Followed by a 1 there, and so we're getting to shorter wavelengths, and that's what they're trying to illustrate here with the wavy line that over here is getting a lot more frequent than it is way over here. You'll notice that the frequency goes from, oh, this was 100,000 up here, 10,000 out to, what is that, a million, hexillion, something like that, 10 hexillion. I can't do it quite in my head there, but you get the idea. We get to a really big energy there, and low low frequency, long, big wavelengths give us low energy. And then over on this end, short, low wavelengths, high frequencies give us high energies. And there's all these different types of light. I will point out that these mostly here are uses of them. The light waves exist on their own. In nature, there are things that naturally emit radio waves, that naturally emit infrared, which is what that one is, that naturally emit microwaves, that naturally emit UV and X-rays, etc., etc. But we've been able to find uses for them. I'll also point out that it is a really narrow band here that is visible light, and that this diagram is not to scale. It's kind of hard to scale it because it's something called a logarithmic scale, but I've heard it said before and kind of trust the calculation that if you're to put your essentially lowest energy naturally occurring and your highest energy naturally occurring across the United States, that the visible spectrum, the part that you and I can see, is about the size of a quarter in Pennsylvania. And everything else is spread out. Of course, that would put the low energy out here in, as a side note, California. I think we're going from LA to New York City in that analogy. And again, it's not a perfect one, but not the scale here at all. Moving on here, a check, they simply ask which one has greater energy. And so looking at this one here, it is blue light has greater energy, ultraviolet light has greater energy, and X-rays have greater energy. It turns out that when we heat up an atom or an element, and we can do that with a flame, as is shown here, or we can do it with with electricity, and we can energize it that way. But no matter how we choose to give it energy, all elements will end up giving off a characteristic color of light. If we take that light and we split it with a prism, or what's called diffraction grating is more frequently used anymore, that light will split into individual bands, and we get what's called an emission or atomic emission spectrum. Sometimes it's also called a bright line emission spectrum. And you get these individual bands of light that are in the same order as a rainbow, but they are discrete individual bands. And it turns out that every element has its own unique atomic spectrum. I'll point out as well that in astronomy, which is one of my big things that I'm a fan of, you will get a dark line absorption spectrum, where instead of the element giving off the light, the element ends up absorbing the light, and so you have the same pattern, except the matching bars end up being these dark spots inside of a rainbow. And not a perfect match there, of course, but you have these dark spots, and then the background is a full-blown rainbow. And so there is what's called a dark line absorption spectra. It's caused by the same thing. Anyway, each element has its own unique series there, because each element has its electron in unique locations. And so then what happens is when we energize those electrons, they jump up to a higher energy level temporarily, because they absorbed that electrical or heat energy or whatever it was, and then they have to get rid of that energy and fall back down to their normal location. And when they do that, they give off that energy in the form of light. If it's in the form of visible light, we can see it. We can use detectors to measure infrared, ultraviolets when they exist, but that is your why, because atoms, it turns out, have different sizes, and so because they have different sizes, even though their electron arrangements will look similar, the actual locations of those electrons is different, which means the jumps of energy is different, which means you're gaining a different amount of energy and losing a different amount of energy, so every element ends up with its own unique spectrum. So just like we mentioned a moment ago, your colors, your traditional colors of your rainbow, Roy G. Biv, your red is your low energy, and your violet is a high energy. And so then each of those lines is associated with a particular electron reaching a particular energy level. And those are assigned numbers that we simply abbreviate with an N for number, and we have them be 1, 2, 3. Naturally occurring, they go up to 7. That includes the non-man-made and man-made elements. Theoretically, we could man-make higher energy levels for the atoms, and they would have higher principal quantum numbers. And you don't need to worry about exactly what that means, but they end up with these energies, and the electrons will start in low energy. If we give them that energy, they can jump up to higher energy. The energy levels get filled up, as we'll see here in a moment, and so once an energy level is filled up, then the next electrons will be in the higher one. If that one gets filled up, they'll be in the higher one, and so on and so forth. It turns out that the electrons can only have certain values, and because of that, we say that they are quantized. That is, that they exist in discrete or quantities. Well, quantities simply means numbers, so now we've already made quantum mechanics more simple because all we mean here is discrete quantities. And to give you an idea, this is like the exact values that we had when we were talking about calculations in sig figs. So, although a gas station can pretend to have a price in the thousandth place, money is quantized. For the American dollar, we can break it up into 100 pieces, and we can't break it up any further than that. You can have a part of a penny, it's not worth anything. If you want to be really picky, it's technically, if you have more than half a penny, you can turn it into a bank and get a whole penny back from it, and then the other half that's less than a half a penny is valueless. And so there are ways to recover damaged money, but you can't, for financial purposes, break it down further than that. You have just a particular dollar amount, that dollar of course including the decimal dollars there, and it exists in discrete quantities. People exist in discrete quantities. You don't have half a person. Certain things are quantized, whereas other things are continuous. How tall a person is throughout their life is a continuous thing that you have to go through every height in between. Now, yeah, you might have a growth spurt where you don't spend long at some of those places in between, but you can be at those different places in between. And so then the energy increases as you get to those higher principal quantum numbers, and I kind of like this bookshelf analogy. I've always seen it as a step or ladder analogy, but the bookcase analogy works really well, and I like it in part because the shelf spacing can be different, which is what it actually matches. I mean, in the real world, the different quantum levels actually have different spacings, so I kind of really like that analogy. I think I'm stealing it for the future. But the electron can either be here, or it can be here. It can't exist in this place in between. Where this differs is, it turns out, and this is weird and you don't have to understand it, and this is where quantum mechanics gets weird and gets a bad name, is that the electron is either here or it is there. That is in one location or another. It doesn't move through the space in between. It's like it disappears at one and instantly reappears at the other. It's weird. Trust me. Trust the physicists who say that's what happens. And the nice thing here is it's quantized, and because of that, we only have to worry about the places where it can be. We don't have to worry about the places where it can't be. So if we want a electron to go from its normal place to a higher energy level, it has to absorb energy. If that higher energy level is nearby versus here where it's far away, then when it falls back down, it's going to release low energy versus high energy light. And the light, although we can imagine it to be a wave, can also be imagined to be particles. And those particles we call photons. And so here we get low energy photons, here we get high energy photons, and the red and green colors there match, the wavelengths match, at least approximations there. And getting rid of that energy is called emitting. And so here we absorb, you can kind of imagine this to be a before, and then it temporarily ends up at these higher energy levels before it emits, and we get our after. Now the before and after in the end are going to match. because the electrons have a normal place that they want to be, like to be. I'm going to personify them a lot, but the normal place they tend to be, and so they're going to go back to that place. This temporary gaining energy is unstable, and they want to release it and end up back at what's called a ground state, their normal position. So here we're asked to list whether it's absorbed, emitted, or there's no change, and so that's how I'm going to do those, because I think the numbers here get confusing with the quantum numbers there. Electron moves from first to third energy, well, that's going to be absorbing energy. Electron falls, that's going to be emitting energy, and an electron moves within the energy level, that is going to be no change in energy. That is not to say that it doesn't have energy. It has energy in the energy level. It's just the amount of energy it has isn't changing because it's orbiting. It's got kinetic energy. It's got potential energy because it's attracted to the nucleus and it's not being pulled all the way into the nucleus. And so it does have energy. There's just not a change in it as it moves around within a energy level. This table is in your textbook and it's fine. It's okay, I suppose. But they don't really explain. So I want to take a moment and explain here and help this make sense and make it so that you can come up with it without having to look it up on a table. The first energy level holds 2 electrons. The second energy level holds 8 electrons. The third energy level also holds 8 electrons. And the next energy level holds the rest for our purposes since we're going to stop at calcium. But it turns out it temporarily holds 8. We then add some to the next energy level before it comes back and it gets more, and it actually goes up to 18. And then some of the later ones actually get up to 32. And there's a shortcut to remembering them, which I'll get to here in just a moment. But from there, electrons start in the lowest energy level. And once an energy level is filled, then they go to higher ones. And they fill, you have to go down here, in energy level or principal quantum number, which I'm just going to use that in abbreviation order. So hydrogen has an atomic number of 1. That means it has 1 electron, so it's the only one that has an electron arrangement of just 1. Helium has 2 electrons, so 2. Lithium has 3, and as a side note, that should be Li. It's a typo in the textbook, but the first one then gets 2 electrons. It's filled up, so the next one gets 1. And then we just keep adding into that second energy level until we get up to 8, which occurs out here at neon, at which point we repeat. The first energy level only holds 2 again, the next one holds 8, it's filled up, so now the next electron, when we get to sodium, has to go in the next column, which also holds 8, and so that's sodium there. A couple things I'll point out here. First off, if we just take oxygen, there's 2 ways I've seen this written. One is 2,6, the other one is 2-6. I have no real preference for either, just so you've seen both. What that means in reality is if we were to draw what's called a Bohr model of the atom, which, by the way, Bohr is the one who discovered this whole emission thing, means that electrons exist on particular levels. So this is a Bohr model. Then the first energy level has 2 electrons. The next energy level here for oxygen has 6. You can space those out evenly, or it turns out later on when we get to something called Lewis diagrams, we'll start to pair them up. So that's how I tend to draw my Bohr models, is with them paired up like that. But there you have it. And that's literally what that means there. This filling up in energy level order that I was writing out over here, that one is known as the Aufbau principle. Aufbau is actually a German word. I was lucky enough to have a German foreign exchange student take chemistry with me years ago, and all the time we'd turn to him because there's actually quite a few German chemists, so we have a lot of terms in chemistry that comes from German, and he was able to say that it means to build up. He said literally it means something like doing layers of bricks to make a brick wall. And so then those layers of bricks, you have to build the bottom layer first. Once you've filled up your wall, then you go up to the next layer. And so it literally means that. The downside is my students often turn to him when we had words from other languages, rich words, and they'd look at him and like, I got no clue either. It was funny. Anyway, from here, this one shows that comma method of drawing it. And so there we have it. Something I want to point out, though, here is if we come back here, notice hydrogen is in the first row, and his electron arrangement is, or excuse me, first row and first column has an electron arrangement with just one. Or sometimes these are called electron configurations. Lithium, same column, it ends in 1. Sodium, same column, it also ends in 1. Potassium, take a guess, same column, it ends in 1. We don't list them out here, but as we go to even higher elements in that column, that is higher atomic numbers, like rubidium and cesium and francium, they all end in an electron arrangement of 1. If we ever discover element 119, it's going to go underneath francium, and its electron arrangement will end in atomic number 1. So that's first shortcut. There, as it turns out, and you can go check this for any of the other columns, except for that last column, helium is an exception. It only has 2 because that first energy level can only hold 2, and helium only has 2 electrons anyway. Everything else in that column, it turns out the noble gases column has 8. The halogens, they all have 7. The alkaline earths, they all have 2. You can go back through here and check that. This one here doesn't have the halogen at the end of the row. The end of that row, I believe, is krypton. And krypton does end in 8 valence electrons, it turns out. The other thing, I mentioned that you wouldn't absolutely have to memorize these numbers. Certainly you can. It's not too hard to remember the handful of numbers. But if you look at the periodic table itself, it has those gaps. And I mentioned previously we'd explain why those gaps are there as we got into other topics. Wow, that's a really wide second column. I think you get the idea for the shape here, though. First row, if you take a look at it, only has 2 elements in it. First period. Second and third period, if you take a look at them, they both have 8 electrons in them. Or 8 elements in them, and it matches the 2, 8, 8 we have there. Calcium, it's right here in the second column of the fourth row. Notice it has 1, 2, 3, 4 numbers, and being in the second column, it ends in 2 there. If you go for just counting the whole number of columns, ignoring those extra rows that are hidden underneath, this works for figuring out their electron arrangements. You just look at where they are on the periodic table, and that using the period number and group number thing that I said we wouldn't use much later on, you can use to figure out the electron arrangement. It's a shortcut. The period number gives you how many numbers are going to be in it. And so, for example, if you're in period 5, then that means there's going to be 5 numbers there. Those lower numbers are all going to be filled up. And so it would be 2, 8, 8. It turns out that this one is eventually 18. Sometimes it starts out with just 8. We'll get into that here on the next slide. And then this last one here is going to be your group number. Again, those transition metals cause some issues with it. This is where using the Roman numeral group number works or is helpful, but again, we're not going to get into a lot of those higher ones. It's fairly easy to figure out the electron arrangement, electron configuration of elements. Once we get above calcium and into the transition metals after calcium, say scandium through zinc, for example, here, there are 10 of them there in that section, but those electrons don't actually go into the 4 energy level. They go into the 3. And so then the 3 gets up to 18, then we fill the next, and then it turns out that pattern kind of repeats. We put 8 in there first, and then we put a couple in the next energy level before going back down and putting more in the prior one before going up, and there's a lot of back and forth there. When it comes to naturally occurring elements, we don't have any elements that have electron arrangements, electron configurations with more than this many in it, but it does theoretically exist, and they can hold higher numbers. And for getting into that, we have to get into other ways to write electron configurations. So it turns out that with the calcium here, the 2, 8, 8, 2 is the simple way. There's also a way that uses arrows and creates what's called an orbital diagram that looks something like this. That's a 2 energy level. Here's a 3 energy level. And this right here, this P and S thing that I'm doing, explains why there's the gaps in those rows on the periodic table. There's then a numeric way to abbreviate this. There's then a noble gas way to abbreviate this. And then there's what's called the quantum number way, and I won't show off there. It's bad enough. I'm wasting your time with this here. If you have me live, I might do it as a exercise, just so you can see it at least in case it ever crops up later on. Here we're asked to do the electron arrangements of these, and yes, you could just go look it up on that table, but I'm going to work it out by hand to show you that it is just doable. So first off, we need the atomic number, and so when we look up the atomic number, we've got 6, 14, 11, and 7. That first energy level can hold 2, the next energy level can hold 8, the next one can hold 8, and the last one I'm just going to word it as holding the rest because we're not going to go above calcium. And so then this one here is 2-4 or 2-4. I was taught the hyphen way. I'll probably do it that way. I'll try to be careful here. The next one we can hold 2 and then 8. That's 10 of them, so the last 4 go there. The next one it's 2, 8, and 1, and the last one here it's 2 and 5. It is not that hard to do. As a side note, these two here are in the second period. And notice that means that they have 2 numbers there on them, and that the last number is their Roman numeral group number. If we look at the other 2, they are in the third period, and they have 3 numbers. The first 2 are all filled up, and then the last one there is their group number. Again, you need the Roman numeral version, or if you look up the group number for silicon and the numbered version, silicon you'll see is actually in group 14, and then you can just drop that 1 there, and it would have been in Roman numeral group 4, and then you have that last digit there. So there are shortcuts to figure them out from where they're at on the periodic table. Again, if you have me live, I might show off and show you some of the higher ones and how you can figure it out that way. Anyway, this here then is trying to come up with a medical application for this. So they're talking about light, and certainly the light can speed up some chemical reactions, and I don't know that that's really tied to those elements gaining or losing that energy as much as it is the bonds gaining or losing energy, or breaking bonds and causing a chemical reaction to happen. And so I don't think that this is a great medical application. I'll also point out that it's a frequent problem here on these is that these should be a line break. It's seasonal affective disorder, SAD, and it unfortunately causes some depression, and so then it makes you sad. It's meant to be punny for choosing the name. I think it's a little bit insulting to those who suffer from it, but there you go. And this one here got cut off, but it's can be treated with a light box by just exposing people to artificial light. Anyway, that finishes up section 6.